Okay, so it's currently recording. So thank you, everyone. Thank you for attending this TCS Plus talk. Before starting, I would like to mention the next talk is going to be 2 weeks from now. It's going to be Nihar Shah from CMU as well, telling us about how to battle demons in peer review. But today we've got Jason Lee from CMU, who's going to tell us about the Karger-Stein algorithm and how it is optimal for Kcup. So Jason is a fourth-year PhD student at CMU, co-advised by Anupam Gupta and Bernard Hublet. Without much further ado, I'm gonna let Jason tell us about his work.
Okay. So this talk is titled "The Karger-Stein Algorithm is Optimal for Kcup," in the joint work with Anupam Gupta from CMU and Yuwing Lee from who's now a faculty at U Michigan. Okay. So in this talk, we'll be considering the Kcup problem. So this is just given a graph, weighted graph, delete the min weight set of edges to split the graph into at least k pieces. So this generalizes the global min cut problem, which is when k is 2. So in this talk, we should think of k as a possibly large constant. So that's the regime where we're talking about. And we want to find the min k cut exactly. Okay. So before we introduce history of this problem, let's consider the min k cut for 2 instructive examples. So for the cycle, the best way to split the cycle into k pieces is just to delete any k edges of the cycle. So the optimum, so suppose every edge has weight 1, then the optimum is exactly k. And what about the number of min k cuts? So which is something else we'll consider during the talk. Well, here you can delete any set of k edges, and this will give you a min k cut. So the number of min k cuts is n choose k. So the other graph that is instructive to think about is the complete graph. So in the complete graph, what is a min k cut? So the best way to split this graph into k pieces is just to chop off k-1 singletons of the graph. So opt is roughly k-1 times n-1. And if we just do that, we double count the k-1 choose 2 edges in between these singletons. So it's roughly n times k. And here the number of min k cuts. So here we can chop off any n-1, the k-1 vertices. So number of min k cuts is n-1 choose k, which is roughly again n choose k. Okay, so in this talk we'll be considering the main two questions we'll consider in this talk are how fast can we compute the min k cut? So this is an algorithmic question. And also how many min k cuts are there in the graph? And this is more of an extremal combinatorics problem. So a brief history on the min k cut problem. So this problem is known to be polynomial time solvable when k is a constant. The 2 most notable results in the history are a randomized contraction algorithm due to Karger and Stein that generalizes Karger's randomized contraction algorithm for min cut. And this runs in time n to the 2k-2. And another result due to Thorup on a tree packing based approach, which runs in also time roughly n to the 2k. Okay. So this year, we were able to combine these 2 approaches and get a algorithm, a rather sophisticated algorithm that slightly beats the n to the 2k bound. So you get n to the 1.99k roughly. And also this year in Fox, I have a result where I improve it down to n to the k roughly, but this only works for unweighted graphs and also unweighted simple graphs, so not even any multi-edges. So what about the lower bound side? It's known that computationally this problem is at least as hard as k cut. Sorry, at least as hard as k clique. And based on popular conjectures on weighted k clique, it's unlikely that there's an algorithm that solves weighted k clique faster than roughly n to the k time, which translates to a similar lower bound of n to the k for a min k cut. And lastly, on the approximation algorithms front, this algorithm is known to be too approximable, even when k is like large, so either linear in n. And also, beating 2 would violate some from well-known hardness assumptions. So what is our main result in this talk? So we generalized both the 1.98 k time algorithm and the n to the k algorithm for unweighted graphs to get a roughly n to the k algorithm for weighted graphs to compute a min k cut. And this algorithm can also enumerate all the min k cuts in the same time. And based on the suggestion of based on the title of this talk, the algorithm we're going to consider is just the original Karger-Stein algorithm. So what we actually show is we can improve the analysis of Karger-Stein to show that actually this algorithm can be run in time n to the k and still output not just one min k cut, but all the min k cuts. So again, this implies an extremal bound of also n to the k. Okay. So before we discuss our improvement, let's begin with Karger's randomized contraction algorithm for min cut for now. So this is just min 2 cut. So his algorithm is very simple. So starting with the original graph, we just randomly pick an edge to contract, and we just keep on doing this until there are 2 vertices remaining, and we take that as our cut. So imagine that's our graph. Suppose it's unweighted for now, just to be simple. Now we pick a random edge to contract each time. So here are the edges that we contract. Ignore the red and white for now. And eventually we get down to 2 vertices. So now for each of the 2 vertices, we consider which original vertices end up getting contracted to that vertex. So the red vertex, we can imagine expanding all the edges back to the red component on the left. And we can do the same for the white vertex. And the red and white becomes our min cut that we consider. And in this case, we did succeed in that we compute the min cut of the graph, which is 3. And a well-known analysis shows that Karger's min cut algorithm will find any given min cut with probably at least 1 over n choose 2. And this is tight for the cycle. So in other words, Karger's algorithm for min cut, the analysis is tight. So what about k cuts? So it turns out the Karger-Stein algorithm is just a straightforward generalization of Karger's algorithm, where we, instead of stopping at 2 vertices, we stop at roughly 2k vertices. And then once we have 2k vertices, we can just brute force over all ways to split the remaining 2k vertices into k pieces. So it turns out a very similar analysis shows that this algorithm will find the min cut with probably roughly, will find any given min k cut with probably roughly n to the minus 2k minus 2. So here, let's do this analysis. It's very simple. So recall that we begin with n vertices remaining, the original graph, and we end at 2k vertices remaining. So we consider the step where there are vertices remaining for each r from n to 2k. And we ask, what is the probability? So let's fix a min k cut in our head. We ask, what is the probability that we actually contract one of these edges of the min k cut? Now, if we contract one of these edges, then we're screwed because we've contracted an edge in opt, and therefore we cannot output opt at the very end. But conversely, if we never contract an edge in opt, then once we end up with 2k vertices remaining, opt will be in there somewhere. One of the partitions will correspond to opt. Right. So suffice it to show that this min k cut survives on each of these iterations where r is from n to 2k. So what is the probability that we fail on the iteration with r vertices remaining? So So again, we select a random edge and suppose the graph is unweighted. So the probability that we fail is just opt over number of edges. So now we use the fact that opt is a min k-cut. I want to claim that opt is at most k-1 times the average of the smallest k-1 degrees, which is also just the sum of the smallest k-1 degrees. So that's just because if we just cut off the smallest k-1, the k-1 vertices with smallest degree, then we get a k-cut. And opt can only be smaller than that. So in other words, opt is at most the sum of the k-1 smallest degrees, which is also k-1 times the average. And the number of edges, the denominator, is just the sum of all the degrees divided by 2, because every edge is counted twice. And that's also just r times the average degree, the average of all r degrees over 2. Okay. So now I want to claim this is at most 2k-1 divided by r. And that's just because in the numerator, I have the average of smallest k-1 degrees. That is clearly at most the average of all the vertices, the average degree of all the vertices, right? So we can just cancel those two out, and we get 2 times k-1 over r. So now, each iteration is independent, whether we succeed or not. So the probability that the opt survives throughout all the iterations is just the product of all the success probabilities, which is 1 minus 2 times k-1 over r. Now we can estimate this with e to the power of minus 2 to the k-1 over r. And if we take the product, then we're just summing over essentially 2 times k-1 divided by n plus 2 times k-1 divided by n minus 1, and all the way down to 2 times k-1 divided by 2k. And we can estimate that by just the harmonic number, the nth harmonic number, which is roughly ln n. So this becomes n times 2 to the minus 2 times k-1. Now note that where did the factor 2 come from in the analysis? It came from the factor 2 here, which itself came from the factor 2 here. We had to divide by 2 because the number of edges is the sum of degrees divided by 2. So that's where the 2 came from. So if you imagine trying to improve this analysis, we would need to get rid of this factor 2. Okay. So now it's instructed to ask, how does the Karger-Stein analysis fare on the cycle and the clique? So let's consider cycle first. So in the cycle, opt is k because we delete any k edges, and the number of edges is r because it's a 2 regular graph. So the number of edges equals number of vertices. But here 2k over r is much less than 2 times k-1 over r. And if we repeat the same analysis, we can replace the 2 times k-1 by k in here. So we get that the success probability is n to the minus k now, instead of n to the 2 times k-1. So in other words, Karger-Stein's analysis is not tight for the cycle. It can be made much better. Note that at any step of the contraction algorithm for a cycle, we still get a cycle because we're just contracting edges. And a cycle always remains a cycle once we contract an edge. Okay. But what about for the complete graph? Well, in this case, opt is roughly k-1 times opt is roughly k-1 times r for the clique on r vertices, because again, it's just we just take k-1 singletons, and each singleton cuts roughly r edges. We're ignoring the double counting for now. And the number of edges is roughly r choose 2, which is roughly r squared minus r squared over 2. And here we get back this 2 times k-1 over r. So in other words, for given a clique, the first time we contract an edge, we succeeded probably exactly 2 times k-1 over r. So in other words, the Karger-Stein analysis is tight. So that might look like bad news. We might ask, how do we beat this factor, which we claim is possible? So essentially, this clique is a worst case analysis in the sense that we're given a graph that's, so this clique example shows that for any regular graph that's like highly connected, we will get this tight answer. But as the Karger-Stein process evolves, it may be that this graph no longer becomes regular. Or it might be that this graph has much higher degree later on. And that's exactly what we want to show. We want to show that as a Karger-Stein process evolves later on, this worst case example just doesn't show up anymore. And that actually what we show is that after a while, most vertices will actually be much higher degree. So here, the degree is n, where n is the, or let's say we start with n clique at the very beginning. So all the degrees are n, roughly. We show that after a while, all the degrees actually become roughly 2n. So this factor 2 turns out to cancel this factor 2, and we'll get k minus 1 over r. Again, I'm hiding a lot under the rug, but that's the intuition. Okay, so let me formally state what we want to prove. What we want to prove is that let's fix any min k cut in our head. We want to show that the Karger-Stein will output this min k cut with probably n to the minus k, whereas Karger-Stein initially showed that was probably n times minus 2k roughly. Great. And our proof outline will consist of two main steps. So first step is first step is an algorithmic statement. We want to refine the analysis of Karger-Stein. And the second statement is it's a more extremal combinatoric statement. We want to show a connection between the cuts of a graph and some extremal set theory statement. So now let me formalize these two claims a bit more. Let's define lambda k bar to be opt over k, which you should think of as the average contribution of each piece of the min k cut to the opt. So what is the more precise statement of precise version of statement 2? We want to show that the number of small cuts, which are defined as the number of cuts of whose size is between lambda k bar and think of this as 1.99 lambda k bar. This should be like roughly linear in n. So imagine k is a constant here, so all of this is a constant. We want to show that the number of small cuts by this definition of small is at most linear in n. And given statement 2, now we want to use statement 2 to refine our analysis of Karger-Stein. We want to show that if the graph G has only linear number of small cuts, which statement 2 guarantees, then Karger-Stein will behave better. So let's begin with the statement 1 first. From now on, it will be more useful to think of the Karger-Stein randomized contraction process as in a more continuous perspective. So here, let's imagine that every edge has an internal exponential clock with rate 1 over lambda k bar. What that means is, that imagine like a very small interval delta. On each time step delta, each edge will independently fire with probably delta over lambda k bar. And whenever an edge fires, we contract that edge. So this is nice. So this is nice in two ways. First, if delta is small enough, then we should not have any ties in the sense that it should not be the case that two edges contract at the same time. So there's an ordering of the edges, which edges get contracted in what order. And this will be a random order because due to the independence. So essentially, we're just running Karger-Stein. In that the next edge that we contract is always going to be uniformly random. But the power that this continuous view gives us is that we can treat each edge as independent of all the other edges. So this was not the case in the original Karger-Stein algorithm because we choose exactly one edge. So these events are dependent which edge we choose. But now every edge is independent. So we want to analyze each edge independently from the others. So now let's repeat the Karger-Stein analysis. To develop some more intuition, let's repeat the Karger-Stein analysis with this independent view, this continuous view of the graph, of the contraction process. So suppose there are vertices remaining. Then by the previous Karger-Stein analysis, that means there are at least r times lambda k bar over 2 edges remaining in the graph. And so how many edges? So every edge in this graph gets contracted with probability delta over lambda k bar. So in expectation, we should expect to contract r times delta over 2 many edges. Again, if delta is like very small, this is like much less than 1. Okay. Now, we want to claim that contracting r times delta over 2 edges is like decreasing the number of vertices by r times delta over 2. This is true as long as we don't contract any cycle, because we want every edge that we contract should decrease the number of vertices by 1. So if the set of edges that we contract has no cycle, then this will be true. But when delta is small enough, when it goes to 0, we should only expect to contract almost 1 edge each iteration. So this should be true. So in other words, in expectation, we should decrease the number of vertices by r times delta over 2. Okay? In other words, r decreases by 1 minus delta over 2 factor in expectation. Now, the first observation is that after t time, which is t over delta many delta time steps, the expected number of vertices that we contract, the expected number of vertices remaining is at most n times this quantity, which is n times e to the minus t over 2. Okay. Now, let's suppose we set t to be 2 ln n. Then this quantity is like roughly 1. So essentially, we're expected to be done by then. So we expect to be done by roughly time 2 ln n. So now, once we're at time 2 ln n, what is the probability that a fixed min kcut survives? So at each delta time step, the probability that we contract one of these edges is the size of the min kcut, which is k times lambda k bar, which we defined as opt over k, times the probability each is contracted roughly, and over t time there's t over delta time steps. So this is roughly e to the minus kt. So this is n to the minus 2k at time t star. Now again, this is not rigorous in the sense that we only have expectation here. So to make this rigorous, we need like a more of a concentration kind of statement that we don't just expect to be finished by this time, but we should expect with high probability that we finish by this time. So this is not formal, but the concentration we'll skip for this talk. So now, how do we improve this analysis? So let's suppose we use our extremal statement that the number of small cuts in the graph, which means the number of cuts within this range, is only linear. And know that this is true for the sanity check. This is true for the clique because the small cuts are just singleton vertices. So now, let's fix one of these small cuts. What is the probability that it survives by time t? That is this expression right here, which ends up being e to the minus t. So now there are n such small cuts. So by linear expectation, the number of cuts that survive by time t is roughly n times e to the minus t. Now if we set t to be ln n roughly, then this n times e to the minus t is 1. So essentially we expect these small cuts to all be contracted by time roughly ln n. Now ln n is less than 2 ln n, and that's where we're getting an improvement. So what about the cuts of size less than lambda k bar? Well, it's a fact that there are most k-1 vertices of degree less than lambda k bar, and that's just because if there are more, then we can just pick those vertices, and this will give us a better cut. So that'll be a contradiction. So that's fact 4. So in other words, by combining these two facts together, in fact 1, that means that after this t star star, which we define as roughly ln n, so all of these small cuts will die out by this time. So the number of remaining vertices, all the remaining vertices will have degree more than this range, which is like roughly twice lambda k bar. And that's where we get our improvement, because initially we said the degree must be at least lambda k bar, but now we have this factor 2 improvement. So we can essentially get rid of that factor 2 in our analysis. So now this only applies from time ln n to 2 ln n. Now by ln n, we should expect like roughly root n vertices remaining. Now, so that means going from root n down to 1 will be a faster rate now than what Karger-Stein originally had. It will be a rate of root n times e to the minus t rather than e to the minus t over 2. So if we just do the naive Karger-Stein analysis up to time ln n, and do the sped up process where now the vertices have double their degree from root n down to 1, this will show that Karger-Stein will contract all the vertices by time 1.5 ln n. And again, we just replace 1.5 by 2. We replace 2 by 1.5 in the original analysis, and that means that we get a bound of n to the minus 1.5k as a probability of any min k surviving. Okay. So now how do we get down? So any questions, by the way, at this point? So this is like the main insight for the algorithmic part of the talk. So to go from 1.5k down to k, so we need a smoother kind of idea. We need a smoother version of this argument. Essentially, we should not be doing the naive analysis from 0 to ln n. We should take advantage of the fact that there are still much fewer. The number of small cuts decreases more rapidly than the number of vertices of the graph. And if we can formulate this smooth argument as a differential equation, and solving this differential equation gives our expectation statement. But again, as stated before, we need a concentration argument to say that with high probability, we end up with with a small number of vertices left. So again, we'll skip this in this talk. Okay. So again, recall that our approach was first we have this algorithmic statement that improves the Karger-Stein analysis given this extremal statement, and 2, we have an extremal combinatoric statement about the number of small cuts on the graph. So in the rest of the talk, we'll go over the extremal statement. So again, this is our extremal statement, and let's first sanity check this statement with again the cycle and the clique. So now for the cycle, so lambda k bar is 1. So here we're asking for cuts of size at most 2 minus epsilon times 1, which is 2 minus epsilon. Now the min cut of the cycle is 2. So there are no small cuts of the graph. So that's okay. Now for the clique, lambda k bar is n minus 1. Now 2 minus epsilon times lambda k bar is just too small for us to cut 2 vertices out of the clique. So cutting 2 vertices goes beyond the 2 minus epsilon times lambda k bar threshold. So we're only left with the singleton cuts, of which there are at most n, of which there are n. Okay, so this statement is sound for these two settings. Okay, so how do we prove the statement? So the first idea is, suppose we consider each cut as a set. Let's just take for a cut, we take an arbitrary side of the cut, and we say, so for this cut, we just take the stuff inside as our set, as our subset of the set of vertices. And now, observe the following. If we can find some k/2 cuts, each of size at most this, whose Venn diagram. So now imagine imposing all these cuts, one over on top of each other, and consider the Venn diagram on these cuts. Suppose this Venn diagram has more than k components, has more than k non-empty atoms. Then this means if we cut these pieces out of the graph, we get a k cut. But how much do we pay for this k cut? Well, we pay k/2 times this quantity, which is less than k times lambda k bar, right? Because recall that lambda k bar is opt over k. So we get a k cut of less than opt, which is a contradiction. So that means that for any k/2 sets that we pick, their Venn diagram must have at most k non-empty atoms. So that's observation 1. Now you might ask, so if we just have idea number 1 in our, can we prove directly that for any set system where this statement holds, that there must be linear number of sets? Turns out this turns out to be false. This turned out to be false. Then there's a counterexample. So we need something else. The second statement we're going to use is something this notion of sunflowers in the extremal combinatorics. So what is a sunflower? A sunflower has a subset of elements called the core, and then another set of elements called the petals, where each set in the sunflower is just the core union of petal. Now, the petals need to be disjoint, and also they must be disjoint from the core. So again, it's this picture. And a well-known statement of Erdos and Rado is that if all the sets are bounded size, then, and also there's no sunflower with a bounded number of petals, then the total number of sets in the family must be bounded. So now in this talk, we will be concerned about sunflowers with non-empty core. So this core could have been empty, but in this case, we do not allow it to be empty. In this case, a simple corollary of the sunflower lemma is that suppose a set system has no sunflower with R petals and non-empty core, then it must have a linear number of sets. Sorry, I guess it also needs to have a bounded size. Everything that's bounded size has no sunflower with bounded number of petals and non-empty core, then the number of sets in the system must be linear. Okay. So now we might ask, one second. So now I want to claim that consider the set system of small cuts of the graph. I want to claim this system cannot have large sunflowers. So that's our connection from sunflowers to the small cuts, the set of small cuts of a graph. So in other words, so we have the following statement. Now for simplicity, let's suppose that we have no cuts of size less than lambda k bar. Again, there was a fact from before that the numbers of these sets can be at most k minus 1. So let's ignore those for now. But the main statement I want to make is that if we take the set of small cuts of a graph, then these sets viewed as a set system does not contain a constant size sunflower with non-empty core. So again, imagine epsilon is 0.01, so this is 1.99. This is a constant size sunflower. So I'm saying this, it excludes a constant size sunflower. Okay. So what is the proof of the statement? Suppose otherwise that there is a large sunflower in the graph with no empty core. So it looks, so again, there's a core, the red vertices, and there are the petals, which are destroying. First, let's imagine contracting the core into a single vertex, and also all the petals into single vertices. Now, so we've assumed beforehand that there are no cuts of size more than less than lambda k bar for simplicity. So if we take the petal as a cut, if you take this cut has size at least lambda k bar. So now once we contract the vertices, we get a single vertex with at least lambda k bar edges out of it. And we repeat the same argument for the core, which we assume to be non-empty. So we get a single vertex here with at least lambda k bar edges out of it. However, we also assume that this set has size at most 1.99 times lambda k bar. So how can that happen? That these two, so this set now has size 2, and these two vertices each have size at least lambda k bar, but this set has size at most 1.99 lambda k bar. I want to claim this can only happen if the number of edges between these two vertices, which if we in the weighted setting, that just means that the weight of this edge between these two vertices is at least epsilon over 2 times lambda k bar. Essentially, we need to double count a lot of edges here. We need to remove a lot of edges from the adjacent to the two vertices in order to ensure that the number of edges going out is at most 1.99 lambda k bar. So now we can repeat the same argument for each of the sets. So each of the petals has at least epsilon over 2 times lambda k bar, many edges to the core. Now we've assumed that this is a 2 over epsilon plus 1 sunflower. So let's consider all the sets except for the bold one. So there are 2 over epsilon such sets. Each set has at least epsilon over 2 lambda k bar edges from the core to this petal. Now all of these edges cross the bolded set. So they're cut by the bolded set. And they're all disjoint because all the petals are disjoint. So in total we have at least lambda k bar. Oh, yeah, this is a mistake. This should be a 4. Everything here should be 4. So in total we have twice lambda k bar edges crossing the cut. So imagine this 2 is a 2 over epsilon to 4 epsilon. I'm sorry if that was a mistake on my part. Then this will be at least twice lambda k bar, many edges crossing, and this will contradict the assumption that this set has size at most lambda k 2 minus epsilon lambda k bar. So any questions on that? Yeah. So then recall the sunflower lemma on sunflowers on non-empty core. It says that sorry, let's ignore that for now. So now finally the extremal statement is as follows. So we call our 2 observations. The first observation is we cannot have, if we view the set of small cuts of the set system, we cannot have k over 2 cuts that intersect in more than k regions. And also, this set system must not have a R sunflower for R large enough. We want to claim that the number of sets must be linear, where we view k and R as constants. So in the base case, let's assume that, so our base case will be, suppose all sets of size at most constant, let's say 5k. In that case, we only need property 2, that there's no R sunflower, so we can just apply the sunflower lemma and get a linear sized number of sets. So second case is, suppose all sets of size more than n minus 5k. Now note that the complement of all the sets should also not have an R sunflower, because these are cuts. So we can take either the set or its complement. Right. So in this case, we'll apply a sunflower lemma on the set of complements, and this is also okay. So in the base cases, if all sets have size at most 5k, or all have size at least n minus 5k, then there are a linear number of sets. So the remaining cases, what if there is a set in the system with size within 5k and n minus 5k? So here, fix one such set of this size, and now consider the following greedy procedure. While we can add a set that introduces 2 more regions to the Venn diagram, do so. So basically, initially we have two atoms in this Venn diagram, just the set and its complement. While we can add a set such that the number of atoms increases by at least 2, then we just add it. So in this case, now there are 4 atoms. So now if we add this set, now there are 6 atoms, and now there are 8 atoms. So we can keep on adding these sets. And suppose that at this point, the process stops. So now by property, by property 1, we must stop at most k regions. So this should be property 1. Why is that? That's because suppose this process continued until there were more than k regions. Then since we add at least 2 regions each time, we must have added at most k minus 2 of these sets. So this will violate property 1, that because we would have found k over 2 sets that intersect in k regions. So that means this process must stop when there are most k regions. There are most k regions in this Venn diagram. And at this point, because we cannot add any other set, that means that every set can either cut a region inside the Venn diagram. So by cut, I mean like it cuts. There's at least one vertex on both sides of the cut in this atom. So it can either cut a region inside or it can cut a region outside, but it cannot do both, because if it cut a region inside and outside, then we would have added it. So what happens if we cut a region outside? Okay, so in this case, this green set here cuts a region outside. It cuts this atom of these 2 vertices. So this atom here cuts this region inside of 3 vertices, where it cuts this one from these 2. So this one cuts, again, this thing. And this does not cut anything outside, because like it agrees perfectly with this atom here on the outside. So this one only cuts inside. And finally, this one doesn't cut anything inside or outside, because it agrees with the atoms in both sides. So now what we're going to do is we want to apply induction. So we're going to split this set system into 2 set systems. We want these to be smaller size at the end. So now what we're going to do is we're going to take the sets that intersected region inside and put them in one of the set systems, and take the ones that intersect outside into another set system. So again, now if it didn't intersect either inside or outside, then we just add it arbitrarily into either one. So now the idea is we want to contract. So for the set system of sets that cut inside, so none of these cut anything outside. So none of these like cut any of the atoms outside. So we're free to contract all these atoms into single vertices. Now similarly, for this set system, there are these. So everything here only cut outside, so it agrees with the atoms inside. So we can contract all the atoms inside and not affect the set system. So now, once we do contraction, we ask how many vertices, how many elements does each set system have? So now suppose this set, the initial the black set that we chose has size S. Then in the top here, we've kept all the elements inside, of which there are S, and the stuff we contracted outside. Now, by assumption, we've stopped at most K regions. So there are most K atoms outside, each of which got contracted to a single element. So there are most K there are now most K contracted vertices outside. So the new number of vertices on this recursive instance is at most S plus K. And by a similar argument, the number of elements in the other recursive instance is n minus S plus K, where n minus S is the number of vertices outside this set that we chose. So now, so what do we have? We have that. So we have that. So we want to apply induction on these two sets, and note that these two sets also satisfy properties 1 and 2, because all we did was safely contract elements and not destroy any sets. So now, if we imply, so if we define Fn as the maximum number of sets on n elements, then we have this equation right here. Okay. Now note that by definition, S is at most n minus 5k. So this quantity here is indeed less than n. So this means that we can safely apply induction. And similarly here, this quantity here is also less than n. So we can safely apply induction to both and solve this recursive formula. And this, along with the base case of a linear sized Fn, when every element has size either less than 5k or more than n minus 5k. So this inequality, along with the base case, will end up solving to linear. Fn is linear. Okay. So that concludes the extremal statement. So this shows that once we impose these two restrictions on a set system, we get a linear size set, and the set of small cuts exactly satisfies these two restrictions. So therefore, the number of small cuts is linear. So let's go back to here. Okay. Yeah. So again, this is a recap of our main strategy, where we refine the algorithmic Karger-Stein randomized contraction algorithm by using this improved bound on the number of small cuts of a graph. And we prove the number of small cuts of a graph by appealing to the sunflower lemma and an argument on set systems excluding a large sunflower. So to summarize, so our main result in this talk was a combinatorial, was both the combinatorial and algorithmic bounds for min k-cut of n to the k. And some open questions are, so can we tighten this bound? By the way, we get the little o1 because our concentration argument is not quite tight, and we pick up this little o1 at the end, which turns out to be like roughly logarithmic, a little bit higher than logarithmic. Now one question is, can we close this gap completely and get n choose k as the number of min k-cuts? So note that we recall that in a cycle, the number of min k-cuts is n choose k. So one other question that is interesting because it's in the intersection of a fixed parameter tractable algorithms and approximation algorithms, is that can we get a 1 plus epsilon approximation to min k-cut in FPT time? So this will break the factor 2 lower bound, but here we are using FPT time, so we're in a stronger scenario. And lastly, we have a randomized algorithm for min k cut. Can we have a corresponding deterministic algorithm for it? That matches the end of the k count. So yeah, that concludes my talk.
Thanks. Is there any question for Jason? Okay, I actually have one question with regard to the extremal statement, like the slide before, but more in a qualitative way. So you prove that, I guess that's tight for your analysis, but is the 1/epsilon tight, you think, qualitatively?
So you mean like just so you're talking about just the extremal statement. So
Yes.
this right here.
Yeah.
Yeah, so this is not tight at all. Like we actually don't, we think this factor here should not be here at all.
At all. Okay.
Yeah. We just don't know how to get past. So we don't know how to get around the sunflower lemma.
Mm-hmm.
So I guess I mentioned that if we take this theorem and only assume property 1 but not property 2,
okay,
this statement is false. So there's an example where there are n square many sets, okay, where only satisfy 1. So we do need some extra property, and it needs to relate to the cusp of the graph somehow. And what the thing we end up finding was sunflowers. But yeah, perhaps like there's like a more clever way to exclude some structure of the set system based on the fact that it came from small cuts, and get a better bound here.
Okay, but like that wouldn't, I mean, that would change this statement, but that wouldn't imply any that wouldn't remove the little of 1 in the exponent. That would improve the constant, I guess.
So that will not get rid of the little of 1. So actually the little of 1, yeah, so that alone will not get rid of the little of 1. We still need to improve the concentration, which I didn't talk about in this talk. It's more technical and it's, I guess, less interesting, less insightful, but it does need to be improved as well.
Okay, thanks.
Hey, Jason, I'm just curious. I guess you said this also works for weighted graphs as well. Is that basically just you sample with the sort of according to the weights and the
yeah. I think the one nice way to just think of weighted graphs is suppose all the graphs have like rational weights. Then we can let's say all the weights are integer. Then we can just replace every edge with like that many multi-edges. Now we're back in the unweighted case. Now suppose the weights are rational, then we just multiply it by a least common denominator of all the weights, and this will be essentially the same graph. And now all the weights are integer, and we can just do the multi-edge thing. So essentially, we can reduce the case where the graph is unweighted. But of course, you're right that if the graph is weighted, a simpler way to analyze Karger-Stein is just to state the Karger-Stein algorithm is just say sample each edge was probably proportional to its weight. Does that make sense?
Yeah, that makes sense. Thanks.
Okay, cool.
Thanks. Okay, so if there are no further questions, I'm gonna take us off air. So let's see. Yeah, stopping the recording.